we're now going to look at some slightly more complicated probability problems. And so what I'm going to do is I'm going to do problems where we roll 2 dice and then add the 2 numbers together. So like right there I rolled a 4. And there I rolled an 11. There I rolled a 6. And there's a 7. And that's an 8. So we're kind of familiar with this because we play games like Monopoly and other board games where you have to roll the 2 dice together and add the numbers. So the smallest number we could roll is a 2, and that would be where you get a 1 and a 1 on both sides. That's snake eyes. The largest number we could roll would be 12, and that's where you get a 6 and a 6. Boxcars, they call that. And so you could get a number from 2 to 12. But now think about this. Is each one of those equally likely? Like, am I just as likely to roll a 2 as I am a 7, let's say? What would be more likely, rolling a 2 or rolling a 7? So if you think about it for a moment, you would be much more likely to roll a 7, right? Because there's like only one way you can roll a 2, and that would be you'd have to get 1 on both dice, right? To roll a 7, I could get like, I could get a 3 and a 4, maybe 2 and a 5, there's 1 and 6. There's multiple combinations that can give me 7. Okay, so some of the rolls from 2 to 12 are going to be more likely than other rolls. And so if we want to find the probability, we got to get behind that. Okay, and in particular, we got to know how many outcomes of that experiment there are. And so the number of outcomes are not just the numbers 2 through 12, those 11 numbers. Those are actually events. And there's different rolls that can give you, let's say, a 5 or a 9 or a 10. Multiple rolls, multiple outcomes can give you those sums, can give you the same sum. And so what we got to do is have all the possible rolls that you could roll, the possible combination of 2 dice rolls. So there's a way of doing this that makes good sense, and it makes it real easy to see what's going on. And that is to make a table. Okay? So we'll say roll 2 dice. We'll say 2 dice and add the numbers rolled. Okay? If we're going to roll 2 dice and add the numbers rolled, I think there should be, there we go. So what I can do is I can make a table, and across the top, this is going to be what I roll on the first dice. I could roll the numbers 1 through 6. And then for the number I roll on my second dice, I'm going to write down the side. Like this. Maybe I'll call this die 1 and I'll call this die 2. So one of these is die 1, one of these is die 2. Sometimes a book will show this by having a red dice and a green dice. And then this will be red dice, this will be green dice. And it does matter. You got to keep track of the 2 dice. You got to treat them as separate dice in order to get the right the right probabilities. Okay? So so basically, if I roll a 1 and a 1, that's my snake eyes, and I would get 2, right? And so this would represent the outcome where I roll a 1 and a 1. So if I roll a 1 and then a 2, I would get a 3. And then if I roll a 1 and a 3, I would get a 4. And you can see that these are just going up by 1s. So then 5, 6, and 7. Okay? So these would be all the different sums I could get if I rolled a 1 on the first dice and a 1, 2, 3, 4, 5, 6 on the second dice. Okay? So then if I rolled a 2 on the first dice and then a 1, I would get a 3 here. And this would be a 4, a 2 and a 2. A 2 and a 3 would be 5. This would be 6, 7, and 8. And then a 3 and a 1 would be 4, 5, 6, 7, 8, 9. 4 and a 1, that would be 5, 6, 7, 8, 9, and 10. This would be 6. 5 and 1 is 6, 7, 8, 9, 10, and 11. And then we would get 7. 6 and 1 is 7, 8, 9, 10, 11, and 12. Okay, so this represents my sample space, this table. And there's actually 36 outcomes. It's like a 6 by 6 square. And if I take 6 times 6, I get 36 outcomes. So each of the numbers in here represent one of the possible rolls. And so each number in here is an outcome. And we can see that several of the outcomes, in this case actually 6 of the outcomes, result in a 7. 6 of the 36 outcomes result in a 7. But only 1 of the 36 outcomes results in a 2. And so you're much more likely to roll a 7 than you are a 2. Does that make sense? So we could find some probabilities now. So when you're at the casino, one of the games is where you roll the dice and, oh, I got an 11. You want to roll a 7 or an 11 to begin with, and if you do, you win right away. If you roll some other number, say I roll a 5, then I got to keep rolling, and I need to roll the 5 again before I roll the 7 or 11. Okay? So either you want to roll a 7 or an 11 at the beginning, and then if you roll some other number, then you got to keep rolling, and you want to re-roll the same number before you roll the 7 or an 11. So that's craps at the casino. So in that case, we might want to know what's the probability of rolling a 7 or an 11. Okay, so this would be out of the 36 outcomes, how many 7 or 11s are there? And there's actually 6 7s. If you notice, there's a pattern. They all lie on this diagonal, right? So there's like these 6 7s and these 2 11s. So there's 8 out of 36, right? And that would be like 2 over 9. It would reduce down. That'd be like 2 repeating. 2, 2, 2, 2. Oop. Okay, so it's like about 22% of the time you're going to roll a 7 or an 11. And you could ask other numbers. Like I might say, what's the probability of rolling an even number? Right? And I could say out of the 36 outcomes, how many are even? Well, the 2... the 4s, the 6, the 8s, the 10s, and the 12s. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 of them are even. Okay? And that is actually 0.5. So in this case, you still have a 50-50 chance of rolling an even number. But that was not at all obvious. Okay? In fact, there's 1, 2, 3, 4, 5, 6 possible even sums you could roll, and there's only 1, 2, 3, 4, 5 odd sums that you could roll, right? And those are not even, but the way that the number of even ones you have does equal the number of odd ones you have. And so it's interesting that you still have 50-50 chance of rolling an even number. Okay? So I don't know if anybody plays Settlers of Catan, but this is exactly what is going on. You have the different tiles that you put on your different regions, and then if you roll the number that's on the tile, you get resources from that region. And so some regions are going to be more productive than other regions because those regions have a higher probability of being rolled. So like the 6 and the 8. Well, first of all, if you play Settlers, rolling a 7 means you have to move the thief. Okay, so that's actually the most likely roll, though it doesn't usually, it doesn't always occur, but that's actually the most likely. And then rolling a 6 or an 8 are the best producing numbers for the regions. And then a 5 and a 9, those are next. That's 4 out of 36. The 4 and the 10, the 3 and the 11, and then the 2 and the 12 are the regions that produce the least. And so if you play Settlers, they have like a tile. Kind of looks like this, and it might have 6. And 6 will actually have 1, 2, 3, 4, 5 dots. If you actually look at the tile, it'll have 5 dots. And then maybe there will be like an 11. And 11 has just 2 dots. Okay? And so the number of dots is actually the number of times it appears in this table. And so you can see how likely it is by looking at the number of dots. And the actual probability would be the number of dots on the tile divided by 36. And that would be the actual probability of rolling that particular sum. So if you don't play Settlers of Catan, don't worry about that. That might be a little confusing. But it is a game where you do roll 2 dice and sum them up, and that's how you gain products from the different regions that you have settlements on. And if you do play Settlers of Catan, maybe this helps you understand what maybe before was maybe a little bit mysterious. This is exactly what's going on for that. Now what I want to show you is that this can be used not just for 2 6-sided dice, but look at this. I have these are 12-sided dice where you can roll them and add them together. So that would be 5. That would be 13. That would be 19. So these are actually 12-sided dice. They have 12 faces. They kind of look like, not quite like a soccer ball, but they have pentagons for their faces instead of squares, and they have the numbers 1 through 12 on them. And you could do a similar thing. It would be a much bigger table, and I'm not going to write it all out, but you would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Kind of squeezed it in there. I should have put it over. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, and then you could do the same thing. This would be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? And you could keep doing this, and you would fill up this whole table. And if you wanted to know the total number of outcomes, do you see how you could do it? This time you have a 12 by 12 square. So it would be 12 times 12. And this time there'd be 144 outcomes. A lot more outcomes. Right? And these sums would go from the number 2. That would be the lowest number you could roll. And then the 12 and the 12 would give you 24. Okay? And that would be the highest number you could roll when you get a 12 on both dice. So 2 to 24 would be the numbers. And it looks like the most likely number is going to be along this diagonal. and it looks like that the one that's most likely is 13. Right? Like 7 was before, this is 13. And it looks like if you count up the diagonal, there's going to be 13 of, 12 of those 13. So the probability of rolling a 13 would be like 12 over 144. Okay? The probability of rolling a 2 or a 24, that would be just like 1 over 144. Okay? And if you completed the table, you could find any other probability that you wanted to find. So in the next video, I'll give you a chance to do this with it's a 4-sided dice, so it'll be a lot smaller table. It'll be even smaller than the 6-sided dice, and these dice look like a kind of a pyramid. So we're going to do that next.